Moving on to today's webinar, what we're going to cover today is no bolts. Sounds counterintuitive, but when you're doing simulation, simulation is a process of making compromises on basically what do I need to include in my simulation versus computational efforts. And a lot of the time, it's not necessary to include bolts. Then we'll discuss using beams to model bolts when we do need bolts in the model. And we'll look at solid models with bolt pretension, how Ansys handles that. Some of the things you need to avoid when using solid models with bolt pretension. And then we'll discuss thread modeling. Today's webinar will be mainly demonstrations. We're going to be pushed for time, so I'll start straight away. We may run over 5 minutes at the end, but we'll see how we go. So let's get started then. Let's look at no beams. And I'm going to start by opening a structural model. I'm going to use in this model the obligatory flange model. Whenever you talk about beams, you use flange model. Seems to be the thing. Just changing this name to flange, and then let's open Ansys. One of the problems with doing these live demos over a webinar is the time it takes for Mechanical to start. We can see down in the bottom left-hand corner, it says starting Mechanical. Should open in a few seconds. And we'll be opening, closing models as we go through the webinar today, so there may be pauses like that as we go through. Okay, so we can see here we've got a flange model. We quite often see customers are modeling things like this. And you can see in this model, we've got no bolts in there. We've just got the bolt holes. If you think about what bolts are, the fasteners, they're used for fastening components together. So as an engineer, when we're doing simulation, we need to decide, do we actually need the bolts in there, or can we get away with fastening these things together using contact? So in its simplest form, the easiest form of modeling bolts is to remove the bolts and model with contact. If we look at the contact in this model, we've got one contact region, the face of the one flange and the face of another flange is the contact region. And this might be okay for this type of analysis. I'm going to go ahead and solve this with bonded contact. We'll record the results and then change the contact status. So the first thing we need to do is put a mesh on there. I'm just going to put a 2mm mesh over the whole of the model. And then I'm just going to be interested in stress on this radius here. So I'm going to insert a sizing control in here, just a little bit smaller, 1.5mm on this area here. In terms of the analysis, I'm going to fix this back face. So we'll go down, structural static, insert fixed support on this back face. I'm going to apply a remote load on this front face. So we'll do insert remote force. I'll apply this remote force an axial distance of 200mm from the face, and I'll put 1000 newtons in the X direction. Now this remote force represents some ancillary equipment that might be attached to this, some loading that we've got some complex modeling here that we don't want to include in the model because we're interested in the flange, but we've included a force. Also, these sort of models, there's usually an internal pressure because this is usually part of some sort of pipe network that's carrying some sort of fluid or gas. So I'm going to insert an internal pressure as well on all the internal faces. We'll insert pressure and we'll insert 10 megapascals. So that's my boundary conditions. Just to recap there, if I select, we've got a fixed support on this face, we've got a remote load representing some extra equipment that's not modeled in this case, and we've got an internal pressure. Let's just have a look at the mesh before we start. So we've got a mesh on there. In a real analysis, I might want to refine this, but for this demo, I think that's adequate. And in terms of results, we're going to insert a deformation, and I'm going to insert a stress value, equivalent stress, and we'll select this face here and just scope it to this face. Okay, and I think we're ready to go. So let's say that's all going. Now this is a purely linear analysis. It should solve very quickly. And I'm going to open a spreadsheet to record the results. So call this flange model. And this first case, we've got bonded back face. And we're going to look at the displacement results and the stress results. Okay, now if we look, the model is actually completed. If we look at the deflection, we can see it's as expected. We've got it expanding because of the pressure and sort of deflecting downwards due to the remote force. And if we look at the stress, we've got a stress in this filling region here. So the stress is 177. Let's put that into our spreadsheet. 177 megapascals. And the deflection is 33 microns. Let's record that in our spreadsheet as well. Now, as an engineer, you might decide that that's adequate results. It's a nice, quick, easy analysis just using bonded contact. It's linear, it solves quickly. And if this is part of a larger network, of a larger model, this might be appropriate if the area of interest is away from this flange. For this particular model, I think this is over stiff, and the contact region might be better if it was defined as a pressure cone. So with a little adjustment to the CAD model, you can imprint a pressure cone on here. Typical standards usually say a 30-degree pressure cone, something like that. I've taken the imprint of the washer because it was nice and convenient. And we can define this as our contact surface. So if I select the surface there as the contact surface, this surface here, actually it's this one, as the target surface. Here we can see we've got contact and target between a pressure cone representing the contact region between around the bolt, 30-degree pressure cone. Now in this case, we've just got one bolt modelled here. We've only created one surface. So we can, let me shrink this a little bit. Oops. Made a mistake again. So I just needed to shrink this because my GoToMeeting control panel was obscuring this closed window. What I wanted to do was we can recreate this bonded contact for each of these 9 bolt holes. Now what we can do this using a thing called the object generator. So what I'm going to do is just demonstrate that. If I hide this body, and what I want to do is select all those surfaces which represent the contact surfaces for the 9 bolt holes. Go down. And I'm going to create a name selection. We'll call these contact surf name selection. And then if I flip the visibility and select the 9 surfaces which represent the target surfaces. Just selecting those surfaces, insert name selection, rename it tag underscore surf. Get my spelling right. Okay, and now I can use the object generator to recreate this one bonded region for the 9 bolt holes. So the object generator is accessed through the automation tab. You can see the button here, object generator. And if I select my contact surface, I get a wizard that allows me to select my contact surfaces, select my target surfaces, and then in order to make sure they match up correctly, I put a between centroids value. Now these contact and target surfaces are coincident, so I'm just going to put small value, 1 millimeter, and then click generate. And here you can see my tree now. If I just close this, in my tree, you can see I've got I've got 9 contact regions representing the pressure cone for each of the bolts. So I'm going to go away and solve that. The advantage of doing it this way, it more accurately represents the contact face between the bolts and the stiffness of that contact, but also it allows me to extract a reaction force that can be used in hand calculations, for instance. In order to extract the the reaction force, I need to specify that the reaction forces are written to the results file. So if I go down into analysis settings and I go down to output controls, you can see here where it says nodal forces. By default, it's set to no. I'm just going to switch that on. And you have to do that if you want to obtain the reaction forces. So let's click solve and just solve this model. Let's open our spreadsheet and just prepare this. Bonded pressure cone, we'll call it. And again, it's still a linear analysis, so it solves pretty robustly. It does require you to create those pressure faces, those imprints to apply those contact regions. And if we look at our results, you can see they're quite different. So we've got 95 microns now in terms of deflection. So it's much less stiff. If we look at the stress, we've got 318. Because we've got more deflection, we've got much higher stress. So from this model, we can see that actually, if we're interested in what's going on this flange rather than a larger model, then it may be more appropriate to use this pressure cone approach here without bolts. Now, reaction loads I talked about, very easy to get reaction loads. If I select my bonded surface, drop it down into the solution branch, we can see we get a force reaction. If I just evaluate that, we can see we get the reaction force here, the direction and the value of that reaction force. We can use that in hand calculations for bolt sizing and so on. Now, there's one other thing I might want to do here, show all the bodies. In this case, and again, this is an engineering judgment, but in this case, if we just look at this animation here, and we can see that obviously there's an outer plane motion here. And if I zoom into the bottom here, where the contact is here, these surfaces here are going into compression at the end of the flange. So there's additional support here that we're not capturing by just using the pressure cone. So in this case, again, it's requiring engineering judgment, and this model might be appropriate for a large assembly, more accurate for a large assembly. But in this case, what I'm going to do is actually model the back face as well as a frictional contact. So if I select one of these contact surfaces, I'm just going to duplicate that and then turn it into a frictional contact. I'm going to give it 0.1 friction coefficient. And I'm going to change obviously this because it's duplicated in this pressure cone surface, but I'm going to change the contact surface to the remainder of the back face. And I'm going to change the target surface to the remainder of the back face on the other flange. So now we've got a pressure cone bonded contact, follow the contact regions where the bolts are applied, and then we've allowed frictional contact for that back face. So in this example, we'll set this going. In this example, this is a non-linear analysis. So now we're adding in complications, and this is where you've got to make that engineering judgment about complications versus computational effort. Do I really need that frictional contact in there? We may not know at this stage. We'll know more when we get the results and see how they compare. Because it's a non-linear analysis, it takes a lot longer to run, and those of you that are familiar with working with contact problems, nonlinear contact problems, or other nonlinear analyses, you know you have to model these. You have to follow the convergence curve. It takes a lot of equilibrium iterations, Newton-Raphson equilibrium iterations, and takes longer to solve. So here we can see it's taken 4 equilibrium iterations already. So that's 4 times the bonded case, 5 equilibrium iterations. It's getting there now. 6 equilibrium iterations. 7 equilibrium iterations. So you begin to see now that those sort of decisions can affect the computational overhead for these type of problems. You know, if this was a large assembly with several of these flanges in, do we need to have this frictional contact in all cases? It depends on the amount of compression you've got between those back faces. So you can see it's taken 9 equilibrium iterations there. And if we look at the deformation, we've now got 104. So if I say bonded pressure cone with frictional back face, we can see now I've got it's stiffer again, and we have equivalent stress of 333. So in this case, we could make the decision that actually we need to include that frictional face, but if it was in tension where these faces are just pulling apart, if there's no out of plane load, then just using a bonded pressure cone may be okay, and will solve a lot quicker than including this frictional back face. So let's just have a summary of what I've just shown there. If we go to using no bolts and replacing bolts with bonded contact, what's the advantages and disadvantages? Well, in this case, when we use the full face contact, very easy to set up. We just brought in the model and the contact was set up, and may be appropriate if you take the view that bolts are used as fasteners to fasten these two faces together. It's also a linear analysis and can be used for linear dynamic analysis because it's linear, but it can be overstiff. You cannot apply bolt pretension, and if you're using the whole of the back face, you can't get the bolt reaction forces. So one step in terms of complexity that you might want to take is define these pressure cones. Obviously, one of the downsides to that, it requires some geometry preparation, but it's still relatively easy to set up. And now we can extract reaction loads and moments. It's still a linear analysis, depending on whether you want to capture that back face compression. But again, the downsides, you can't in this model without modeling the bolts, you can't model pretension, and it requires some geometry preparation in terms of imprinting those pressure cone faces. So let's talk about using beams. So let's open our model. So we might want to use beams to join this model together. So this time, instead of using this bonded contact, I'm going to suppress this bonded contact and just show you how you use beams. So in this model here that we had before, now you create beams by connecting a beam that represents the bolt to a particular surface or edge. Again, I've got these imprinted faces that represents the washer. So you can attach a beam to these faces here. So if I go, how we do that, if I go into connections and do insert a beam, we create a beam object, and the first thing we need is two faces. So down here we have the reference face. It's already attached it, but I'm going to do it again manually. So I'll select this face here and click apply. And further down in the object, we've got this mobile face, and I'm going to select this surface here and click apply. And now we can see we've got a beam in the model that's attached. This beam has real material properties. It's steel in this case, and it has a radius. I'm going to make it 3.5. And here we can see now we've got a representation of bolts that has stiffness and is attached to those surfaces. Now, obviously, we've only got one here. We can use the object generator again to recreate that bolt for the other bolt holes. So again, I need to go in and create a name selection of all those reference surfaces this time. So we'll just zoom out, select those reference surfaces, 9 of them. And we'll go in and create a name selection. And we'll call these reference surfaces. And then I can create another name selection which represents the, I'll just start that again, I think I made a mistake there. Which represents those target surfaces. insert a name selection, rename it target surf. And now I can use that object generator again. So we select the object we want to regenerate from the tree that we want to multiply, automation tab, object generator. Now, because I'm using a beam as the object I want to recreate, it's asking me for the reference surfaces. It's asking me for the target surfaces, the name selection. And here I put a distance between centroids. Because we're using the outer surface of these flanges, it's a little bit larger. So I'm going to use 15 millimeters and click generate. And now we can see that we've got all those 9 beams generated there. And we can go ahead and solve this model. Before solving, I have to remove this reaction load that was remaining from before. That's because it's connected to a pressure cone contact that we've now removed. And actually, one step that I missed last time was, actually, no, I didn't miss a step. Let's just solve this. I'm okay. Let's do a solve. Let's close the wizard. And while it's solving, we'll just set up our spreadsheet ready to record. And again, we've still got that frictional back face to stop that compression loading between the back face and the bottom edge. So it's still a nonlinear analysis. We've got beams in there. So it still uses a number of iterations to solve to a solution. We could open a book at this point and start laying bets on how many equilibrium iterations we think it's going to take. Hopefully this model is pretty well behaved, so it should converge pretty quickly. One of the things you may be noticing, because we've got a large number of constraint equations, when you use beams, we're using constraint equations. I'll show what that looks like in terms of a spider after the solution. But each equilibrium iteration takes a little bit longer. So again, we're lengthening the run times, we're creating complexity. Up to 6 equilibrium iterations, 7. It's getting there. Hopefully it'll be there soon. 8. One more iteration, I believe, and we should have a solution. For those of you that do these types of analyses, this is quite a nice curve. You want to see convergence like this. And there we've got some results. So let's have a look. The deformation in this case, we've got 128. So we go to our spreadsheet. And if we look at stress, 353. So again, because we put bolts in there and the bolts have material stiffness and we've applied no pretension, it's again less stiff than using the pressure cone, and we've got more deflection and a higher stress. Now what I'm going to do is we're going to discuss pretension next, and I'll come back to this model and run it with pretension. So let's just return to the presentation briefly, talk about using beams. Again, beams are easy to set up. They can be used with frictional contact. One of the pros is you don't need to model the bolt and nut geometry. We quite often see solid geometry brought in. You don't need that. You can extract bolt reactions for use in hand calcs and can be used with bolt pretension. Let's just return to that actually. If you want to obtain the reaction force, you can select on one of these bolts and again just drag down into the solution branch and do evaluate all results. Here we can see the reaction forces, shear loads and so on that can be used in hand calculations. They can also be used with bolt pretension. We'll come back to that. For a large number of bolts, they can be fiddly to set up, and it doesn't include complex interaction between friction, complex interaction between the bolt head, the nut and the washers, and the flanges itself. And actually, that's the only reason why you should use a solid model, is when you want to obtain that complex interaction. One of the other things, just before moving off this model, I wanted to show you, I mentioned I would show you. If we go to the solution information branch and just click on the geometry tab, we can see how these beam models are modeled internally within Ansys. So there's a series of remote connections between the end of these beams. It models a Spider-Man beam network. Let's just move on to a solid model with pretension. So the next stage is, when do we include a solid model? When do we actually have a model of the bolt with a bolt head and a washer? So if we go back to I'm going to add on a new analysis. Well, we won't use the flange model for this. I'm going to use, call it bracket. And I'm going to attach a bolted bracket. So we've got a bolted bracket model. Let's just open this model. So again, we've got a little pause while the model opens. You can see down here it's saying starting mechanical. So here we've got a bolted assembly. For those of you that's attending some of my non-linear webinars, it's the same model we use in the non-linear webinar. I'm just going to remove, there's a sheath around the bolt here that I'm going to suppress, take that out of the simulation. So here we've got a bolted model. We're interested really in stressing this bracket, and we're going to apply a bolt pretension to this. And we want, when we include a bolt model, it's really because we want to look at the detailed interaction, what's going on between the bolt head and the washers. Does it affect the results of what we're interested in? So in this case, let's set up a simple analysis. I'll select these surfaces and just fix those. So insert a fix support. And then applying a bolt pretension, it's a case of just selecting a cylinder, a cylindrical surface that represents the bolt shaft, and insert a bolt pretension. You can apply a load or an adjustment. In this case, I'm going to apply 1,000 Newton load, and that's all you need to do to apply a bolt pretension. For a mesh on here, I'm just going to put a 2mm mesh on here. And we're really ready to go with this model. Just let's insert some result items. So I'm going to insert deformation, and then I'm going to insert stress, equivalent stress on this bracket only. And before I set this going, again, for the reaction loads, if we want to extract reaction loads, we need to write out the nodal forces. So we need to turn this no to yes. We need to write those out to the results file. So let's just have a look at the contact before setting it going. I'm not going to change anything here. And actually, before we do that, I'm just going to simplify the naming convention here, just so I can see these better. This is practice I use a lot. So I'll name that bolt. I'll rename that bracket. So these are the three components I'm interested in, and I'll rename this top washer. And then if I go down and I rename my contact branches based on definition, I can see here the interactions I'm interested in. So at the moment, it's all bonded, and we're going to go away and solve that as a bonded simulation. So let's create another entry in the spreadsheet for recording results. And this first analysis, we're doing a bonded contact, so it's all linear, should solve pretty quickly. And there we've got results. So this is results with bonded contacts. I'm just going to animate these results. And if we zoom into the center of the bolt, this demonstrates quite well what happens when you apply a bolt pretension load. At a solution level, Ansys cracks the bolt shaft. It creates a crack through the model. It slits the model along the element edges. See, it's quite a rugged, if you like, surface. Then he applies pretension elements. If you want details of the pretension elements, they're called Pret 179 elements. You can look in the Ansys documentation of those. And then he applies a pretension. So you can see these two halves where we've got that crack, they look as though they're passing through each other. Obviously, this is exaggerating this analysis because the deformation is scaled up. But it quite clearly shows what's going on with pretension. And it's pretty important that you understand that's how it works. If we just go in and look at the top part here, we can see this remains bonded through the analysis. And this is probably incorrect in this case. There's probably gaps opening up here that affect the results. So we're going to show that next. So let's just record the results in our spreadsheet. The deformation, 605 microns. And the stress in the bracket, 292 megapascals. So let's see what happens when we change the contact type. So this top washer, let's have a look at the contact between the bracket and the top washer. Turn the mesh off so we can see that better. And here we can see the contact is bonded. I'm just going to flip that contact. Generally, I like to see the larger surface, and the surface that is, if you like, opposing the motion is the target surface, and the one that's moving into the target surface, the contact surface. So I think this is a better definition. And we're going to change this to frictional contact. So we'll go down, frictional, so it's 0.1. And just so this converges better, I'm just going to change the stiffness, the contact stiffness. Now, I don't necessarily recommend this. Again, it's another decision, but generally speaking, with these sort of models, the softer the stiffness, the better it will converge, but you may get some penetration. I'm also going to switch on adjuster to touch. These two parts should be coincident when you bring in the model, so I'm going to model it as though they're coincident and just switch on adjuster to touch. And we'll go away and solve that model. So now we've brought in more complexity into the model. We've now got a complex non-linear interaction between that top washer and the bracket. We think it should affect the results. And that's the only reason when you think that interaction should affect the results of what you're looking at, then that's when you should include the bolt and the bolt head. One of the things I will point out, it's not always necessary. As you can see here, we've got a nice representation of bolts from CAD. We've got the hex shape here. We've even got a chamfer on the top. It's probably not necessary to do that. It's probably suffice just to represent the bolts in this case with a cylinder as a head. You know, interested in the reaction load down here. Putting in this detail just adds extra detail that's not needed. So if we look at the convergence curve, we can see here now it's not converging greatly. I mean, it's coming down, the number's coming down. You can see it's taking a lot of equilibrium iterations. So the question you've got to raise here is, do I need these bolts in my model? You're adding a lot of computational effort to the model. Do they need to be there? Can I get away with beams? Can I get away with just using contact? Do we want to place a bet on when this will converge? Come on, place your bets now. Is it going to keep coming down? It's looking good. It's looking good. It's getting there. There we go. The magenta lines cross the cyan line, and we should have convergence. We've got a forced convergence. There we are. So if we look at the deformation in this, we can see now it's much larger. 1.19. Frictional. And the stress is 374. So that's a perfect example of when you should really include the bolt head, the washer, when you think that interaction is going to make a huge difference to the results, as it did in this case. Before moving on to the next section, I just wanted to talk about obtaining reaction loads. When you have a solid model like this, you can obtain reaction loads by creating a construction surface through this beam. So I'll just show you do that. First thing we need to do is create a coordinate system. We do that by inserting a coordinate system, selecting this cylindrical surface. We want the construction plane to be aligned with the XY plane here, so we need to rotate the model. So I'm going to select Z-axis aligned with the global X, and we also probably want to offset it a little bit here because we don't want that construction plane to be in the same location as the pretension mesh split. So I'm going to put 15 millimeters in here. And now what I can do is go to Model, Insert Construction Surface. You can see it's aligned that with the global coordinate system. So I change it to the local coordinate system. And now we've got a construction surface. And we can go down to the results, insert a probe, a force reaction probe, and we can attach this to a construction surface. I'm selecting the surface. I select the construction surface name, and the geometry is the bolt. Apply, and if we evaluate those results, here we can see we've got a force reaction on that construction surface through the center of that modeled bolt shaft. So let's just close this model and move on to the next section, which is, let's just discuss the pros and cons first. Working with a solid model really can include the contact interaction between bolthead and nut, and that's really when you should be including it. One of the other pros, and we quite often see, this is one of the main reasons why people have solid bolts in the model, is because they come straight from CAD with them already there and don't require any geometry preparation. I think you need to be a little bit more intelligent. Make a decision on whether they need to be there, whether you can get away with not using them. Obviously, adding bolts increases the run times, adds complication, adds to the computational overhead. So try and remove them if you can. One of the other things is you need careful consideration of the pretension location. So what do we mean by that? And I'm just going to demonstrate that. So if we go back here, I'm going to use a third model to demonstrate it. Bolted tooth, call it a tooth model. Let's open this model. I am running a little bit behind schedule here. I do anticipate this just to run for maybe 5 minutes beyond 12 o'clock. But we'll see how we go. Okay, again, I've got another type of bolted model here. We've got a tooth with a back face, and we've got two machine screws, cap head machine screws, if you like, cap head bolts. What I want to do, I'm just going to rotate and create a section plane, and let's just look at what's going on in here inside the model. So if I rotate this round, for these sort of models, we have a threaded section which is represented by the green bolt and the grey part of the tool. So this interface here is bonded. And then typically we have a clearance section. So this back plate is not bonded to the bolt and is generally modeled with a clearance in there. So one of the first things you need to do with these sort of models is make sure that that contact is representative. So I'm just going to go down and have a look at the contact in this model. Again, let's rename, I like doing this, rename based on contact. And if we look at the contact here, we can see that Ansys automatically has created bonded contact across that clearance face. So just to fix that, I'm going to go in and I'm going to change the default tolerance that Ansys uses. So I'm going to set this to 0.1. I believe that gap is 0.2. So I'm going to set it to 0.1 and just ask you to recreate that automatic contact. And now if we look at this contact, we can see it's what we want. So it's just the bolt back face and on the back face. So that's the first thing you need to make sure is that the contact represents what you want. Okay, in this analysis, we're going to use those machine bolts to nip that tooth up to the back face. So in terms of setting up the analysis, we're going to insert a fixed support on this back face. And we are going to insert, hide this model on one, show bodies, hide body. I'm going to insert a bolt pretension on here. Again, we'll use 1000 newtons again, as we did in the other model. Bolt pretension on this bolt. (1000 newtons). The contact between the tooth and the back face here needs to be frictional. We need to allow that to move away if required. So I'll put 0.1 as a friction coefficient again, so it solves quickly. Just for demo purposes, don't necessarily recommend you do this because it can compromise the accuracy, but I'm going to make the contact a little bit softer. And again, I'm going to use adjusted to touch because these two surfaces are supposed to be coincident at the start of the analysis. Let's have a look at the mesh. We're going to meshing. Now what I'm going to do is put a silly large mesh, coarse mesh on here. Let's do generate mesh. And if we look at this mesh, just hide this body, see here a pretty coarse mesh. And this is one of the first problems you need to be careful of. I quite often get sent models by customers and they say, Ansys is telling me it can't create bolt pretension. If you remember when you're creating bolt pretension, you're splitting or cracking the mesh at a pretension location. You need to have enough elements in your model. So if you're taking in a large solid model with bolts in there and putting a coarse mesh on there and thinking it will work, you need to be more careful about the amount of elements you have in the bolt. So let's just change the mesh density. I'm going to put 2 millimeters and then 1.5 on the bolts. Insert a sizing control on the bolts. Let's put in 1.5 millimeters. Generate the mesh. And if I switch on section plane and just click on show element edges, we can see the mesh now on that section plane. Now we've got enough elements to create the pretension section. So let's go away and solve that. I'm just going to insert a deformation. Let's show all bodies. And let's go and solve that. Again, let's put the force convergence on. Look at the force convergence. We could do what most engineering analysts do at this point when they're waiting for something to converge. Go away and browse the internet and see what's going on in the news. Let's not do that in this case. Okay, we've got one equilibrium iteration. Again, this is a non-linear analysis, so it does take multiple equilibrium iterations. If I've set this up as I did in my practice, it should converge very quickly. So the force convergence should have converged. It's taken an extra iteration, so that's setting off alarm bells for me in this model. Something's gone wrong. It should have converged here, but it's taken an extra iteration. Let's have a look at the results. So if I look at the results, let's animate these. Now this is the second problem you need to avoid. You can see here that Ansys has put the pretension cut at the bonded region. So instead of pulling this tooth towards the back plate, it's actually pulling it away from the back face. So this is the second thing that you need to look out for when using pretension in solid models. You need to make sure that that pretension cut occurs in an unbonded part of the bolt shaft. How do we do that? Let's just go back to our model. Let's hide this back face. So there are a couple of ways we can do this. In this case, we want that pretension to occur around about the middle of this unbonded section. So one of the things we could do is go back to our CAD system and split this surface and then just apply the pretension to this surface. If we don't have access to the CAD system, we can use a coordinate system to define the pretension location. So let me just demonstrate how you do that. If we go into coordinate systems, we'll do insert coordinate system and we'll attach that coordinate system to this cylindrical surface. Again, we need to rotate that local coordinate system so the z-axis is aligned with the shaft axial direction. So the z-axis is aligned with the global y. And then we need to offset that coordinate system so that it's in the location where we want the split to be. So I'm going to select 14 millimeters. So that looks pretty good. If it's Ansys splits the mesh here, that looks fine. So now if I go down to my bolt pretension, I can use that coordinate system to define the split location. And to do that, select the bolt as the geometry rather than the shaft face. And now I've got a coordinate system, so I can go down and select newly created coordinate system. And we can see it's applying it in the right location. I can repeat that for the second bolt. Select the coordinate system. Now I can use the same coordinate system because the XY plane is essentially infinite. So I can use, even though it displays it in the wrong location, it actually applies the split correctly. So let's just go away and solve that. Let's see what the difference is. So we have another one of those pauses while it solves. We go back and surf the internet. Spend a few minutes looking at the news while we wait for that to solve. I think that's the usual sort of behavior of simulation engineers. Maybe watch YouTube for 10 minutes. Okay, we can see the forces converged almost immediately. And it hasn't taken that extra iteration, so things are looking better already. Let's show all bodies. And let's have a look at the animation. And we can now see that Ansys has put the split where we wanted it to be. You can see that tooth is being pulled nicely onto that back face, which is what we want. So, gotchas with solid modeling. Remember that Ansys creates an internal split, and it's usually places that is approximately halfway along the surface that you've selected. It needs to be fine enough for Ansys to be able, the mesh needs to be fine enough for Ansys to be able to create that split. And you need to ensure that split line occurs in a part of the shaft where it's not bonded. There is always a non-bonded part of the shaft. So those are the gotchas when using solid models. Let's just return for a moment to our beam model, our flange model. If you remember the last time we ran this, we didn't apply a pretension. So now we've discussed pretension. Let's see how we can apply pretension to those beams. And this is quite easy. You select the beams from the tree, and if we just drag those down into the environment branch, the structural static environment branch, you can see the bolt pretensions are automatically created for each of those bolts. Now, when you're doing an analysis like this with bolt pretension and external loads, you normally do it in 2 steps. So I'm going to do a 2-step analysis. The first step, we apply the bolt pretension load. So if I select all the bolt pretensions for each of the bolts, I select step 1 and I can enter a value. I'm going to put 2000 newtons in this case. And then I select step 2 and I'm going to lock those bolts in position in step 2. Now, if I go to my loads, the remote force, I want this to be 0 in the first step while I'm applying the bolt pretension, and then I apply the remote force afterwards. Again, with the pressure, 0 in the first load step and 10 megapascals in the second load step. And actually, I'm just going to change one thing from the previous analysis just because we're running out of time and I want it to converge quickly. I'm just going to select this frictional back face and just soften the contact in here. I'm going to select factor 0.1 and I'm going to put in adjusted to touch. That should just help it converge a little bit better. And let's solve this model with pretension and see how that compares to the beams with no pretension. Now, if we think about not using beams at all, using this pressure cone where it's joined together with perfect contact, if you like, we get this value here. We think that possibly could be over stiff because beams actually have stiffness in there. The beams or the bolts they represent have stiffness. Now we think this one may be under stiff because we haven't used any pretension. So this one with pretension in there should fall somewhere in between these two values. Let's see how the convergence is going. You can see the first load step appears to have converged very well. So moving on to the second load step, we can see here down the time, first load step time in 1 second, second load step time 2. So we've applied the pretension, now we're applying the remote load and the pressure. Solution's nearly there. And we've got some results. So the deformation in this case, 123, let's see how that compares. And the stress is now 353. So you can see by adding pretension, the deformation, it's deformation we're interested here mainly. We can see it's now somewhere in between what we thought was the understiff and the overstiff solution. So it could be pretty accurate. So that's how you apply, if you like, bolt pretension to beams as well as solid models. The last bit I want to discuss today, and we've got 5 minutes left, it may take a little bit longer, is virtual thread modeling. So if you think no contact is the low end of the spectrum, which is always should be the goal, can we get away without the beams and just using contact? Did I just say no contact? I mean no beams, no bolts, and modeling it with contact. That's where we should be trying to get to if we think it's accurate enough. At the other end of the spectrum is actually modeling the full bolt with its thread. And we see people trying to do this. So I've just got a couple of models here. I'm not going to solve these ones live because they're quite big. So I've got 2 examples here. The first one is we've got a bolt and the thread is actually modeled. It's a full 3D solid model. We've modeled a bolt, we've got a solution, and we're calculating the stress and the deflection with the thread in there. Let's just wait till this opens and we'll see the complexity in that model. So it is basically a bolt with a nut. In terms of loads and boundary conditions, we fixed this face and applied a force on this face, 1000 newtons. And we've calculated the deflection. Here we can see the deflection. And we've calculated the stress. In this case, we're plotting the stress in the bolt. If we look at the mesh, switch on the mesh, you can see the mesh needs to be huge in order to capture the stress in those areas. This is a huge mesh. I think it's got about 1.2 million nodes. Solving that is quite considerable. So obviously you don't go to this level of detail in your large assembly models. There's no need to do that. Occasionally with specialized bolts, we do get customers that need to model the thread and what's going on in the thread, and they're actually designing the thread. And that is the only time you really go to a thread model, when you're designing the thread and want to understand whether the thread will be stripped, for instance. Now, in this second model, we're using a technique which Ansys introduced a few years ago, called virtual thread modeling. So it's the ability to be able to model the thread stresses without actually geometrically modeling the thread. And you'll see what I mean when this second model opens. So if we look in this second model, you can see my solid model, my CAN model doesn't have the thread in there. That means when I mesh it, I can get away with a lot less elements. I still need to have quite a coarse mesh on here. If we have a look at the mesh, actually we can see it's still quite fine. But the mesh count in here is approximately a third of the previous model with the elements in there. Applied to the contact surface. So if I look at the contact surface here, between the nut and the bolt, so I'll just show the nut in the model, we've got a contact and target surface. On that contact definition, if we go down here, we can see we have this branch called geometry correction. I can specify that the geometry correction is I want to model a bolt thread. You can put in the pitch diameter, the pitch distance, the angle, whether it's single threaded, right-handed, and so on. You need to use frictional contact as the contact type, and also you need to change the detection method. So the default detection method is usually Gauss points, and that doesn't work for this virtual thread modeling. In this case, I've used nodal normal to target. When we solve this, we look at the results. The results are almost identical. I mean, there we're plotting deformation. And if we look at stress, we get a nice thread pattern in terms of stress. And this is calculated by applying this geometry correction based on ideal thread conditions. You can see here we've got 75 megapascals. Let's see what we had with the full thread. So I think it's this one I want, 88 megapascals. So the results are in the same ballpark, pretty similar. There's probably, as we refine the mesh on this model, refine the mesh on another model, these values will become close together. So that's virtual thread modeling. If you do need to go to the extent of modeling threads, you can make use of this virtual mesh, virtual thread modeling, which reduces the computational overhead again. So bang on 12 o'clock, just come to the summary slide. We're coming to the end of the presentation. You know, when you're modeling bolts and bolted assembly in Ansys, the more detail you include, the more computational overhead you have in the analysis, the longer run times you have. So the whole process of modeling bolts is using engineering judgment to decide what I can get away with. If you can get away with just using contact to model, then it will solve a lot quicker. You'll get a lot more robust solution, but you have to be aware of the compromises. One of the things you shouldn't be doing is using virtual thread modeling or even true thread modeling, on large assemblies. You'll never get a model that computationally efficient to solve. So try to keep it as simple as possible. Start with no bolts and move to virtual thread modeling, depending on the case. You have to use engineering judgment. There's no hard and fast rule. It may require some trial and error. Adding unnecessary complexity increases the run times, computational times. If you're using solid models, and we see a lot of this, make sure you've got enough elements to model the pretension split. I can't emphasize this enough. Numerous occasions I've had models sent to me by our customers. I'm getting a message, Ansys cannot create bolt pretension. It falls over before even starting. And it's because they've got a large number of solid bolts in there. They've applied pretension, but they've got a relatively coarse mesh on those bolts. If you're using a solid model, make sure the bolt pretension is in an unbonded location. So that's the end. We haven't run over too much, maybe rushed in the last few minutes, but that's the end of today's webinar. Those are the techniques we see being used out there in the field for modeling bolts and bolted connections. So if there's any questions, I will leave 5 minutes for any questions. I think if you type them into the chat window, Ellen will be picking them up.
Hi, Chris. Yeah, we've had quite a few questions, quite a variety of questions, and I've tried to answer as we've gone along, and said that you'd probably get in touch post the event. Some of them are quite specific. So yeah, it's probably best to handle it that way if that's okay with you, Chris.
Yeah, that's fine.
Okay, if anybody's got any more questions, if you'd like to post those in the question chat box, they do get recorded, and Chris will get back to you as soon as he possibly can.
And again, if you've got any questions that you want to discuss directly, just get in contact with us. Any sort of simulations that you may have that you're having problems with and need advice, get in contact with us and we'll see what we can do.